Dear students and parents, if you want to receive authentic and relevant information for various competitive exams, please like and subscribe to my channel and like my Facebook page Nigam Sir's IIT Rankers Institute. Thanks. Today we are going to discuss IIT JEE Advanced 2020 Paper 2 Question number 1. A large square container with thin transparent vertical walls and filled with water, refractive index 4/3, is kept on a horizontal table. A student holds a thin straight wire vertically inside the water 12 cm from one of its corners as shown in the figure. Looking at the wire from this corner, another student sees two images of the wire located symmetrically on each side of the line of sight as shown. The separation in centimeter between these images is. So here this is the container filled with water, this is the wire, and it is being seen like this. So this is the line of sight. Now if we try to solve this question within JEE syllabus, considering the case of normal incidence, we will get answer as 3. However, rays at normal incidence will not reach the eye. If we consider those rays which after refraction travel approximately parallel to the given line of sight, then the answer may be 4 or 5, as we have to consider integral values only. Here is my solution to this problem. First, we should recall the result for apparent depth at oblique incidence. So if this is a refracting surface, this medium is having refractive index mu and the other medium is air. Object is in the medium at point O. The depth of the object is capital D, and this is the observer, such that rays travelling at an angle of incidence I get refracted at an angle of refraction R to be seen by the observer. Now if we take another ray at an angle I plus Di, it will get refracted at an angle R plus Dr, and producing these two rays backwards, the image will be formed at point I. The apparent depth is small d, and the image is also shifted parallel to the surface of incidence by a distance f. If we do detailed calculations, then we conclude that small d is capital D by mu cos cube r upon cos cube I, and f is capital D tan I minus dy mu cos cube r upon cos cube I into tan I, where capital D is real depth, small d is apparent depth, f is the shift in image parallel to the surface of incidence. Now this is the figure and this is the line of sight. Now rotating this figure by 45 degree anti-clockwise, the container will become like this, and this will be the observer, and this is the line of sight. Now a ray travelling at an angle of incidence I will get refracted at some angle R and reach the observer. We will have the relation 4/3 sin I is 1 into sin R. So a number of values of I and R are possible for which after refraction the rays will reach the observer. However, I will consider a case where the rays after refraction are approximately parallel to the line of sight. So we will take R as approximately 45 degree. Now if I take R as approximately 45 degree, then 4/3 sin I is 1 into 1 by root 2. Sin I will be 3/4 root 2, and cos I will be root 23/4 root 2. The depth capital D will be 12 cm cos 45, 6 root 2 centimeters. So here we have the calculation. 4 by 3 sin I is 1 into sin 45 equal to 1 by root 2. Sin I is 3 by 4 root 2 and cos I is root 23 by 4 root 2. Sin 45 is 1 by root 2 equal to cos 45 and that is cos R. Now suppose this is the object and rays are travelling like this to reach the observer and rays are travelling like this to reach the observer, and the images are I1 and I2. I1 is at a distance d below this surface and I2 is at a distance d from this surface. Also the images are shifted by a distance x along the surface. So note that the images I1 and I2 are at a depth d below the surface of incidence and are shifted a distance x parallel to the surface of incidence. Now by geometry of the figure, if you apply geometry, I1 I2 will be equal to root 2 into square root of capital D minus small d minus x. Please note, capital D minus small d minus x, the square root of this quantity multiplied by root 2. Now small d will be capital D by mu cos cube r by cos cube I, so it will be 6 root 2 centimeter upon 4 by 3 into 1 upon 2 root 2 upon 23 by 4 root 2 root 23 by 4 root 2 cube. So this, if you solve and calculate, this will be approximately 3.69 centimeters. So this means that the image will be at a distance of 3.69 centimeters below this surface or from this surface. Now x will be capital D tan I minus d by mu cos cube r upon cos cube I into tan r. If you do the calculation, x will come out to be approximately 1.62 centimeters. Now d is 6 root 2 centimeters, so it is 8.484 centimeters. Capital D minus small d minus x is approximately 8.484 minus 3.69 minus 1.62 equal to 3.174 centimeters. Now I1 I2 is root 2 square root of capital D minus small d minus x, and that is approximately 4.48 centimeters. So as the answer is coming 4.48 centimeters and we have to choose integral values, then the correct answer may be 4 or 5. So we can take the answer as 4 or 5. Now alternate solution using normal incidence, although not appropriate for given line of sight. Here, if this is the object and this is the image, and if this is the object and I2 is the image, then I1m and I2n is the apparent depth. So it will be 6 root 2 centimeters real depth upon mu, so 6 root 2 centimeters upon 4 by 3, that will be 9 by root 2 centimeters. Now OI1 and OI2 will be OM minus MI1, so 6 root 2 minus 9 by root 2 centimeters. So OI1 will be equal to 3 by root 2 centimeters and that will also be equal to OI2. Now I1 I2 will be, by Pythagoras theorem, root 2 into 3 by root 2 centimeters, so that will be 3 centimeters. So one more answer considering the case of normal incidence can be 3 centimeters, although rays at normal incidence will not reach the eye. So that is why the answer has been taken as 3 centimeter or 4 centimeter or 5 centimeters. Thank you.